Now within ERA interim, some of these variables are analysis variables like temperature, but others are forecasts, and some are available every 6 hours, and some are available every 3 hours. Within ECEM, we'll be providing these gridded data sets at the 6-hourly or 3-hourly time step, depending on the variable, for the whole of this domain, and we'll be providing them as the original data, our interpolation of ERA interim, and also as the bias adjusted ones. And we'll also be providing through the demonstrator and for the demonstrator these averages of these variables across 33 European countries and a bigger number of clusters within Europe, which have come from the eHighway 2050 project. So the variables we'll be looking at are these ones. I've mentioned them: air temperature, and we'll look at the maximum minimum as well. These are all 6-hourly, and some are more daily though in concept. Precipitation, solar radiation, wind speed, and relative humidity. Now, to get relative humidity, particularly in the observational sense, we need to use dew point temperatures as well as air temperatures. We will be looking at, not in great detail, but at some other variables of relevance to energy, particularly river discharge and water temperature. And we're working with another of these Copernicus Climate Service projects called SWICA in that context. Now, what are the observational data sets we've got to look at comparisons with the reanalysis? Well, there's been a number of data sets produced, and the main one we're going to be using is a data set called EOBS, which is produced by the Dutch Met Service KNMI. And this produces gridded fields of daily maximum minimum air temperature and precipitation totals on this 1/2 by 1/2 degree latitude-longitude grid. So that's the main one we'll be using for those two variables. There are data sets also on temperature and precipitation on a monthly basis from the Climatic Research Unit and also the Global Precipitation Climatology Center, which is part of the German Weather Service. And they're on the same grid as EOBS, but they're monthly. They have use in looking slightly further back in time and in areas of sparse observational coverage. And then, but for wind speed data and dew point temperatures, we don't have a gridded products. And here we're using a data set called HAD-ISD, which is the Hadley Center International Surface Data Set. And this is of sub-daily measurements of a number of variables, including wind speed and dew point temperatures, which goes back to the mid-1970s. So you can download this data, and there's several hundred stations across Europe. For solar radiation, though, there's not the same quantity of measurements around Europe. And so we're using the limited number of stations that are available. This is 55 stations. And we're also using satellite data looking at Europe from above, which enables you to estimate the cloudiness better and so produce a better observational database. So we've had a number of workshops within ECEM, and we talked about the data availability, the 6-hourly and daily data within ERA interim, and the reasons for bias adjustment. So this bias adjustment is performed in Work Package 2, and the results will be used in Work Package 3 and 4. But there's potential use outside the energy sector as well. Now, one of the issues in this is whether the bias adjustment is worth doing. It might introduce more errors, but one way of assessing its usefulness and its need is to use these ESCIs that Alberto discussed earlier within Work Package 3 to see whether they're improved by using the original ERA interim data or the adjusted, and we'll be doing that in the coming months. Another issue in bias adjustment is whether the intervariable consistency is important in the energy context. So what I mean here is that when it's in winter, when it's warmer temperatures in Western Europe, it tends to be cloudier. So there tends to be less solar radiation when it's warmer, and you tend to get more solar radiation when it's colder during the winter months, and the opposite happens in summer. So there's this intervariable consistency that could be important, and this comes to the issue of bias adjusting, whether you do this on a variable independent basis, or are there key pairs that you need to adjust in some sort of multivariate way. Now, from the two workshops, it's clear that a lot of the users we have of climate data are mainly interested in a single variable. So they're less interested in these multivariate adjustments. We're still doing work on this, but what I'm going to present today is treating each of the key variables as independent from each other. So I'll move on now to the bias adjustment itself, and we'll be looking at the gridded observational data over land areas. So what we're doing is just over the land where the observational data are. It is possible to look at wind data for some of the wind farms and the tall towers in some parts of the North Sea, but that's a sort of separate issue at the moment, and we may come and do some more work on that. The bias adjustment I'll be talking about is just for the historical period from 1979 to 2014 or 2016, and but you also need something similar for seasonal forecasts and also for climate projections, and I'll come back to that at the end. And the way you might do this, the approaches are quite different for seasonal forecasts compared to the projections, which are more like the historical adjustments that I'll be talking about today. Now, bias adjustment has been around some time. It developed from the need to adjust climate model output, both global climate models and regional ones. And one of the first adjustment techniques that was put forward was simple bias adjustment, where you adjusted the data on a monthly basis, adjusting the monthly average or the monthly total based on comparison to observational data. This could be a gridded product or it could be station data. But in ECEM, we're much more interested in daily and subdaily timescales than monthly averages. And this is why intervariable relationships might be important. Now, the reanalysis have these relationships, and they're very good. And so this is where the issue comes in of, if you bias adjust, do you reduce or alter those intervariable relationships? And one way we have of looking at that is through the use of ESCIs and seeing whether the bias adjusted results produce better energy sector variables. Now, there's a number of approaches to bias adjustment in the literature. As I said, they were introduced to bias adjust GCMs and RCMs, but some of these even use the reanalysis as the method of adjustment, so assuming it's perfect. Now, the recent methods include quantile mapping, equating the cumulative distribution functions, or some distribution plus scale approach. Now, our approach is similar to the first two, and it's also distributional in nature. So if you think back to the Whedon work in the WATCH project, that is adjusting the mean, essentially. Here we're adjusting the mean and the variance in a way, so we're improving the distributional plot of era interim compared to observations. And the approach we're following is this paper by Tai et al., in which they're altering the shape and scale parameters of the Weibull distribution for wind speeds in order to make era interim look better compared to observations. Now, what you can do with the example I'm going to show is for wind speeds, and the Weibull distribution is a common distribution used for wind speeds, and it calculates the distribution of wind speed data in terms of a shape and a scale parameter. So here, we're comparing the value calculated for an era interim grid box with a nearby station, and on the left you've got how that compares for the scale parameter, and on the right you've got how it compares for the shape parameter. And it's a reasonable comparison. There are obvious differences, often in more mountainous regions, often in coastal regions, and often the data quality that we're comparing with the observational data is not as good as we would like it to be. So there's a number of reasons why some of these FITs comparing observations with ERA interim are not as good as they possibly could be. So what we do in effect in this analysis is to take the observational parameters for the Weibull scale and shape parameters, and then make them become the ERA interim ones, and then we sort of normalize one and then renormalize it or denormalize it, going back with the shape and scale parameters from the observations. So when you do that, you start off with this level of agreement, and then afterwards, having adjusted ERA interim, you get this level of agreement where you're getting many more of the shape and scale parameters are almost exactly the same as the adjusted ERA interim in terms of their observational values. There's still a few stations where the fit is not ideal. They tend to be more in mountainous regions and coastal regions, but the vast majority of stations are fitted very well with this adjusted fit to ERA interim. Now, what this does to an individual station, you can see here. So this is the distributional fit with the Weibull distribution in terms of the CDF for observational values here for January, February, and March for the station at Kirkwall Airport on the Orkney Islands in the north of Scotland. And it's based on all the 6-hourly 10-meter wind speeds during each of those 3 months. And the black line is the observations at 10 meters, and the brown line is the ERA interim values for the nearest grid box, or the grid box that contains Kirkwall. And then the green is what the adjustments do. So you can see how they move the adjusted reanalysis data to have the very similar distribution compared to what it did have with the observations. And within the scientific paper we're working on, which we hope to submit in the next week or two, this is just one station in 803, and all these fits will be available for all the months of the year, along with all the adjusted and the original ERA interim data. So for the other variables, we're following a similar procedure, but we're using a different distribution. Because the Weibull is a good distribution for wind speeds. The air temperatures and dew points are much more akin to a normal distribution, and we're doing these to get the temperature ones themselves and also to calculate relative humidity. And then a gamma distribution is used for precipitation, and this also seems to work quite well, although there are more issues with this working not as well as temperature and wind speed, simply because the distributional fits for precipitation, particularly in the summer months in southern Europe, are quite difficult to fit because there's very few days of precipitation in some of the summer months the further south you move in Europe. The observational data, the dew point temperatures have to use the Hadley ISD dataset again, and air temperature and precipitation use the EOBS dataset that I talked about. So the final variable we're going to look at is radiation. And there are not gridded data sets for this, and there's very few observations of this in terms of direct measurements of the ground. But when you compare ERA interim here for a station in the southwest of England at Camborne, you've got the daily irradiation from ERA on the y-axis here, and then the calculation at the station. And you can see it's approximately a one-to-one line, but there's a lot of scatter in the plot, and the correlation is not that good. If I were to show you a similar plot for a station in Egypt, then you would have a very good agreement, and that's simply because the cloud doesn't occur very often in Egypt, whereas over southwest of England, it's important to get the cloud right, to get the radiation right. And really, it's an issue of getting ERA interim to get the cloud right, and then it will do much better at getting the radiation right. So effectively, we've developed a technique to take a satellite data set called HelioClim, which is available from 2003 to 2012, and then to relate that with regression to the ERA interim, and then apply those regression relationships back to 1979, and then we can then compare them with these station data we have plotted here from the 55 locations across Europe and North Africa. And as I say, we'll be writing all this up in a scientific paper, which will be submitting to a journal fairly soon. Now, some gross results here. Overall, ERA interim slightly overestimates radiation across Europe, but there are differences, and these are seasonal as well. But spatially, ERA interim is overestimating some radiation in the more northern regions in the Baltic. It's slightly overestimating in sort of Western Europe, and it's underestimating a little bit in Eastern Europe. But with the adjustments, these will be put these will be improved as we move to the adjusted data set. As I said, the seasonal forecasting works in a different way, and here we're concentrating more on these key variables, but more at the national scale and at the cluster scale. So we'll be developing a lot of relationships, and also at the seasonal scale, between the key variables like wind speed and radiation here. And climate projections, which we haven't done much work on yet, there'll be a similar approach to the historical, possibly using the bias adjusted reanalysis as the thing to adjust to. The same variables, we'll be using the CORDEX RCM simulations, and the emphasis will be more on the daily time scale, which is what CORDEX actually archives, although some of the variables are archived at 3 and 6 hourly as well. And our chosen future is going to be the period 2035 to 2064, which will be used in the demonstrator that Alberto mentioned. So the conclusions are here. We're going to update the work fairly soon in the beginning months of next year to use the full ERA interim period from 1979 to 2016. We're then going to be looking in 2018 to adapt this to the new ERA reanalysis, ERA 5, which will be on a finer spatial resolution. We've done some experimentation with wind speeds measured at towers in on the offshore sites, particularly in the North Sea. And for this, you needn't use the surface estimates of wind speed from ERA interim. You can also use the lower levels of the troposphere, and particularly with ERA interim, the level 58 winds. These are winds at about 60 to 100 meters height above the ground, and it seems they work better in comparison to tower measurements, and they're potentially more relevant to the tall wind generating towers that we see in many parts of Europe. The seasonal forecasting is going to use EuroSIP, which is the currently accepted seasonal forecasting timescale, but there'll be changes to that during the project as ECMWF improves those. And as I said, the basic adjustment approach we're going to apply will be to the CORDEX, and we'll do the same thing for the projections. So thank you very much.
Thank you very much, Phil.
You can take the screen back now. Yeah.
Yes. Yeah. We'll now switch over to Robert, who will start his presentation. And in the meantime, please feel free to ask your questions on the control panel. There's a tab with questions. Over to you, Robert. Thank you.
Yes. Hello, everyone. I hope this technically works and you can see my presentation on the screen. I make it full screen. Is that okay?
It's okay for me.
Yes.
Okay. So thank you, Alberto, and I would also like to thank the SM team for giving me the opportunity to present what we are doing on climate projections. And I'm the lead of the other energy project, which is called Clean for Energy, and I was helped by a number of persons for making these presentations, which are listed in this slide. So climate projections in general aim at answering the question of how the climate, the statistics of the variables that were talked about in the last presentation evolve with time and with changes in external forcing, which can be natural forcing or anthropogenic forcing, greenhouse gases, aerosols, land use changes, etc. So, for instance, I put on the figure, sorry, I need to mask this. I put on the figure one of the major figure of the IPCC Working Group 1 that was released in the assessment report 2013, which is the projection of climate until 2100, which is made under several socioeconomic scenarios which induce different greenhouse gas emission scenarios. So basically, this picture shows how the mean temperature over the globe is likely to evolve with uncertainty range in these scenarios. And now the idea is that all these climate projections could also be used in other sectors and to discuss and predict the weather and climate that would occur in other variables and in detailed regions. So, as you may know, the climate projections are based on global Earth system model, which includes both the ocean, the atmosphere modeling, and other components such as land cover, land use, and the carbon cycle and other chemical compounds that are present in the atmosphere and that are important for the change of climate. And they all include these components together to make a projection, to make a simulation that would start back in the 19th century, and that would go actually beyond the 21st century in general. However, these models are usually of two-course resolution to be useful for climate impacts and climate change impacts, especially in various economic sectors such as agriculture, but also energy. And therefore, we need some stages before doing the impact calculation, and usually there's a downscaling stage which is done by limited area models, which have the advantage of having a much higher resolution, typically of 10 to 50 kilometers, but the drawback of having a limited area only, and therefore this is the way usually impacts are calculated. One thing to mention is that in all regional climate projection we should not use a single model, because models have their own uncertainties, and uncertainties are very important if we look at one model only. And usually impact studies are done using an ensemble, or even sometimes several ensembles of models, which actually requires a coordinated effort internationally. So currently, many teams have gone together to try and downscale the global climate projections that are available in the CEMIP experiment, to make them more regional and to have ensembles at relatively at a scale which is relevant for impact. And this is really the Cordex framework, which has now been set up a few years ago. So I will be, in the rest of my talk, focusing on Europe, but everything that is said on Europe can be done also on other regions using other setup of other Cordex domains. So Yeah, so the Eurocordex framework, which was focused for Europe, had the uniqueness to propose 12 kilometers, so very high resolution, relatively high, sorry, resolution models, which also cover a scale of 5,000 kilometers wide, which is covering all Europe and a bit of north of Africa. So there's also an unprecedented number of model simulation with common framework. I said 10 models, actually it's an order of magnitude. And we have to think these are not only models, but pairs of models, because this is a GCM coupled with a regional climate model and different greenhouse gas scenarios. And it's really interesting because it covers a lot of possibilities. We'll see examples. It's been evaluated in a number of studies. There has been evaluation work of this data as such, and I would like to recommend to read all these papers. So as an example, we can see, for instance, how these models simulate future heat waves. And as an example, I took here the temperature evolution, the summer temperature evolution across the last 60 years, which is the left panel, and the heavy line, heavy black line, which shows the temperature around Paris. And the peak you see is the 2003 heat wave. And it's nice to see how this value of temperature, of thermal temperature, can be found in climate projections. So there's a lot of simulations shown in the two right hand side windows, which show actually about 10 simulations in each case, showing a world, how the temperature around Paris would be in a 2-degree warmer climate or 3-degree warmer climate, and showing that, for instance, in a 2-degree warmer climate, such a heat wave would appear with a frequency of less than 1 year out of 4, but in a 3-degree climate, it's going to be almost almost 50% of summers would reach this value in a 3-degree climate. So this could have also some implications, of course, for the energy sectors. And this was done in the previous project, Impact2C. And in this project, we also investigated how renewable energies would change in such scenarios with a 2-degree warming and 3-degree warming. And the plot shown here shows actually what is to be expected using several models. So the bars show the average of the models, and the individual points show the models. And the blue shows a 2-degree, and the red shows a 3-degree time period. And what we see is that for all countries, or most countries in Europe, the wind power load factor, which was calculated in this case using a wind farm fleet equal to that of 2013. So this wind power load factor would decrease on average. So it is expected to decrease by a few percent. So not much, and with some uncertainty. But we do see still a significant signal. So what we have done in this now in the Clean4Energy project is try to kind of generalize this study, and we have produced so far climate data set which is tailored to the energy sector, which contains almost all variables that were described by Phil in the previous presentation. And it has a high resolution of 12 kilometers, a 3-hourly time step for 4 of the variables. And it contains, for the moment, 10 models. It will include more models in the future, and it's been bias adjusted. So it's a different type of bias adjustment, because here we're talking about the bias adjustment of the climate projections, not of the reference data set. And also it contains a methodology to select subsets of these data sets according to some criteria that I can describe a bit later. So we had the first release on July 2016, and we expect to have a second release on the beginning of February 2017. As for SM, we also are in the process of writing an article on that, and on the specific aspect of the climate projection. So the climate projection has been corrected using the WFDEI data, and it will progressively be replaced by improved reference data, as was shown by Phil, especially data coming from the SM project. And the bias adjustment here is specific because it needs to include also bias adjustment for the future climate for which we do not have observation. So the method we use, which is the cumulative distribution function transform method, uses a way of transforming data and taking into account the non-stationarity of the climate, which is taking place in the model simulation, not in the observations, because we don't have future observations, of course. So it also includes a frequency correction for precipitation, which is has been published recently in Vrac et al. In 2016, and an adaptation also to high resolution, which allows to bias correct at high resolution per kilometer as well. So now, at the moment, we could look at how this bias corrected data set resembles the observations. So what we try to do is not using a gridded data set, because a gridded data set has already been transformed from direct observations, but we use the ECA and D for temperature and precipitation as a kind of verification of the distribution. So we look at, for instance, some statistics before adjustment and after adjustment, and we could see that, for instance, for the mean absolute bias, which is the absolute value averaged over all 485 stations, we have an improvement of a factor of 2 of the mean absolute bias, and about the same for the extremes, so the quantile 5 and the quantile 95. And we have also calculated other statistics, which shows that the bias adjustment does really correct the values. So, however, this is bias adjustment has been made on the basis of daily or 3-hourly values, and what we are not entirely, I would say, entirely confident at the moment is whether the data keeps the same consistency in the longer time scales, such as monthly values, and we will be investigating this in the near future as well. We are also investigating station comparison for all the other variables. So the wind, also with station data at 10 meter, and radiation data. So this will be compared also with satellite data for wind over the ocean. So it has been done in several studies before, and we can do it also this study. And so there's a lot of evaluation going on at the moment, and we intend to publish that as soon as we can. So now I'm going to, in the remainder of the time I have, show just a few applications. So the first one has been brought actually by our colleagues from Météo France, who are using the data in Clean4Energy, and they have looked at the evolution of the solar potential for 2050 and between now and 2050, between now and 2050, and as an example, show the here the solar capacity factor evolution calculated on the right-hand side from now to 2050 with a decrease of the solar capacity factor, which is due to several factors, of which the main is probably the increase in water vapor in the atmosphere, but also the increase in temperature, which makes the panels less efficient. So the solar capacity factor changes are actually quite robust in many models, but we can see also that not all models are simulated the same amplitude on the left-hand side. So on the left-hand side, it's actually for different countries, but you can see that in many countries in Europe, we are expecting from these simulations that the solar capacity factor will decrease in the winter. I must add that this is for the winter season. And not all models are simulated the same amplitude. One model is simulated almost no change, and some other models are simulated a much larger amplitude of this type of change. A second type of application is the energy sector is often facing adverse events. So I'm talking here about, as an example, about cold spells, and usually have reference events such as the winter of 1963, which was an extreme cold, or 95, and see how these events, what would be the probability of such an event currently and in the future, because it could be important for dimensioning the infrastructures. So here I show a risk curve, which is actually an indicator on the which is a heat indicator, an average over 30 cities of the temperature. So it goes here from -5 to +8, and it's the average over January months. And on the horizontal line, it's the return period. So it's the inverse of the probability. So it decreases as the cold temperature decreases with the return period. And what is shown is two curves from the climate projections. The risk curve for the 70 to 2000 period, and the risk curve for the current period, which could be taken, for instance, as the 2001 to 2030. So it's these climate projections allow to have not one realization of the climate, but as many as we have models, in this case 10. So for 30 years, we have actually 300 winters, 300 January months, and we can make statistics that can go in the extremes a bit better. So what we see is essentially that the climate is warming in the simulations, and that, for instance, an event of a mean temperature of 0 degree would actually, in the current climate, occur much less often than in the 70 to 2000 period. So I put here the reference event of January 85, which was an event with a probability of with a return period of 50 years, and to show that in the current climate, it would the probability would be divided by 2. I can show also observations put on top of that to show that it fits quite nicely with the model, and also the future climate for which, for the same event, we could expect a decrease of probability by a factor of 2. So quickly to finish, we have envisaged and we are planning several other applications in different subsectors of the energy sector, and we'll provide indicators for each of those, going from bioenergy, wind power, hydropower, etc., and even waves and sea level, high sea level heights for the offshore assets that will be indicators at the end of this year. Sorry, this coming year, so at the end of 2017 we expect. Then, I don't have time to go through that, but we also have a method for subsample selections. And to end, I would like to emphasize that the data sets will be, and actually are already available on the Earth System Grid Federation international network of data centers providing climate projection data, not only climate projection, but climate projections like CMIP, CORDEX, and other types of projections like EasyMIP and Clean4Energy and other projects. So it is really available, and quality control, standardized, and this is the overall aim of this distributed network of data distribution. So thank you for your attention, and we would like to welcome anybody interested to visit also our website, which is indicated at the bottom. Thanks.
Okay, thank you very much, Robert. That was great. And we now have some time for questions, which I've been collecting. We don't have very many, but I'll be switching now over to my screen. So I'm showing here the questions that have been asked. There is one for Phil.
I don't think you show the screen, your screen, at the moment.
So
you do now.
Yeah. Okay. So you can see now the questions.
Oh, the screen's gone again.
It should come up soon.
Oh, okay.
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 So it should be there now. So thank you for the questions, for the questions from the attendees. So we have one question from for Phil, and it's: how do you interpolate the bias corrections outside stations when stations are scarce?
So what we're doing here is we have each station is in one of the ERA interim squares, and we're using the ones that are inside the squares for those ones. But for the ones, some of the boxes don't have stations, so we're using a number of stations around the area. So we're using a few stations to interpolate the adjustments that we're making to the distributions. So we're interpolating the shape and scale parameters from the stations to the ERA interim squares. So I don't know if that answers your question, Robert.
Yeah, that was my question. yeah, that does perfectly.
Yeah.
Okay, and we have a question for Robert. By the way, while you listen to if you can manage also to type your questions while you listen to the answer, please go ahead and type your questions. So Robert, the question for Robert is: what is the definition of cold events used Is there a duration of the event associated with the amplitude?
Yes, I must apologize. I've been quickly to this on this point. Here, in this case, we define the cold event as a monthly low temperature. So what was shown on the y-axis was the return value, was the heat index of monthly temperatures of January, and that was for January. So taking the example as the January 85 as a very low temperature over France.
Okay, that's very good. Now we have a question for both. So if I understand correctly, both projects will provide their data to the energy sector, which is probably not as familiar with the technicalities of bias correction. Will there be detailed user guidance documents available that explain the application and the limits, the do's and don'ts of these bias correction methods? Who wants to go first?
Okay, I'll go first. Essentially, they will be providing the data. I think I said for the ERA interim data, we'll be providing the grids over the whole domain. So the original data and then the bias adjusted data. And we'll also be providing these as averages across the countries and also across the clusters. So that's a number of sub-regions of either France or the UK, for example. And hopefully there'll be a paper that will get published in one of these newer data journals, but we'll also be providing some guidance documents along with that, because we'll be providing the data before the paper comes out. We will include some of the do's and don'ts for how you use these data. And we will build on that as the project goes along. So we bring back the results of with the ESCIs to look at the usefulness of the bias adjustment in this more downstream energy variable, as opposed to the wind speed or the solar irradiance data.
Excellent. Thank you, Phil, for your answer. I guess Robert also wants to provide his view on this.
Yes, we intend to. So at the moment, for the climate projections, we have released it for beta testing, but now in early 2017, these will be tested and more operational data. So these will be provided with guidance on the one hand for users, and on the other hand with scientific paper, which will most probably also be submitted to a journal, an open access journal, which could also show the submitted paper, not only the accepted and published paper. So we intend to do both, to do both this and but in the guidance there will be a kind of summary of the methods used, not going into big details, and the what to do's and what to not do, the do's and don'ts. I think that's been written like that. We expect that in the end of January 2017.
Yes, and it's also possible for users to contact either of the projects to ask specific questions if they want. So just send emails and we will endeavor to respond to those.
Okay, thank you both. I think we have actually a last minute question that I can try to copy quickly. So I think it's on, it's for Robert, and I'll put it under you. So the presentation.
I don't see it at the moment.
Yeah, it's coming. The presentation was mentioning the impacts of cold weather events on the energy sector. Any example of practical impact of extreme heat on the energy sector? Question mark. Thank you.
Yes, of course, there is a lot of impacts, and there has been several studies, and we can do the same for the other extreme. We can also do the same for low winds, which are also a problem for the sector as well, for low radiation as well, because then there could be difficulties to match demand. And we have one web package in Clean for Energy which is dedicated to that as well. So all types of extremes that could be relevant for the energy sector will be covered. And I would like also to mention that there has been papers on heat waves impact on electricity, thermoelectric production. I can advertise from our colleagues from the University of Wageningen recent papers if somebody is interested specifically to the extreme heat case.
Okay, thank you very much, Robert. That was a nice conclusion to the question, and I would also like to add, referring back to the question on the provision of information to the energy sector, that both projects, ESOM certainly, but also Clean for Energy, will have a demonstrator which will have, as I mentioned briefly before, this demonstrator will have a visual component, so you can display the data but also download the data, and also get information about the data. And in a broader term, Copernicus Climate Change Service Program also is interested, in fact is their scope, mandate, to provide this type of information in the long term. And so they are setting up what is called a climate data store, which will include all the information we are showing here, and with all the information. And if you haven't been able to ask your question, or if you're interested about learning more about these issues, what's better way to come to Barcelona on the 22nd and 23rd of February, where we'll have a symposium. The two climate service projects, ESOM and Clean for Energy, are jointly organizing this symposium, which is going to run for 2 days, and you'll find the program on our website, and you can also already register. Registrations are open through the Eventbrite site. So I encourage you to have a look at the program, which is quite exciting, and we'll look forward to seeing you there. And if you still want to know more, there is also another event that is actually at international level, even broader, looking at the energy meteorology. This is the 4th conference of the series, and is going to be held in the south of Italy from 27th to 29th of June in a very nice spot. So again, I encourage you to look at the website and come back to us if you have any questions. These are the dates for the submissions of abstracts and registrations. There's also a WEMC Young Scientist Award that is being launched, and that will run in parallel with the conference. So if you submit your abstract by the deadline, and if you within the scope of this award, you're very welcome to apply and get more also information on the website or through emailing us. To conclude, I'd just like to give you the reference for our projects. So the ESM project at the top, Clean for Energy project following, and also the World Energy Meteorology Council, which has been supporting these initiatives. And we also have these two Twitter handles that you can use to be informed and keep in the loop with what we do. Thank you very much for your attention, and we look forward to seeing you at one of our events or at one of the webinars, or just getting in touch by email. Thank you very much. Bye-bye.
Alberto, I'm still online. Do you want to have an organizing session?
Yeah, briefly. Yeah, there's. I was just waiting to. I had to dismiss the participants. Yeah. So they're all gone. Yeah. So went well. I thought it was.
Yeah, I'm just discovering all your